is my pleasure to introduce Sebastian Fernández for his Ph.D. defense today. I think this is, in general, this group of students is really had a hard task ahead of them. Starting in their first and second year with the pandemic and trying to build connections, build their research up in a virtual way. And Sebastian decided to make that even harder on himself by joining a brand new lab that was also starting in the middle of the pandemic. So not only was he coming into a new place and trying to learn, he also came into an empty room, people trying to figure out and build it for the first time. So just to give a sense of the degree of difficulty he's facing. And as a new professor, you sort of plan for a lot of things, right? You recruit students and all of those things. Sebastian was unplanned. Sebastian emailed me out of the blue, looking for a spot in the group. He actually has been at Stanford a year longer than me, so he's technically the longest tenured member of our research group here at Stanford. Great. And so I said, yes, we'd be happy to come on in. We can show you what we're doing. We can teach you. And right away in those first couple of quarters, two things became really, really evident. First of all, that Sebastian had no idea what we were doing, right? He had never been in the glove box before. He hadn't worked with some of the materials we were working with before. And so we really started from the very basics and had to kind of build up from nothing. But the second thing that became really evident was that Sebastian was just going to push and push and push and push through these, right? Unlike a lot of students who come in and kind of know the field very well, he learned from the ground up. He pushed through all of these challenges, learned all those little tips and tricks of the trade that come with experimental work, to the point that now he's the super user of almost all of the equipment in our group at one point or another. He's the person that everyone goes to for those tips, for those tricks. And I think that process of sort of starting from the bottom and coming up really showed. And I think it will also show in his research here, because there was numerous points through these research projects where you sort of just have to push and push and push and bang your head against the wall. And he pushed through and persevered in a great way. And I think that will show through in some of the excellent work that's here. I also want to highlight here that beyond all of this great work, Sebastian has done a ton of mentorship for the department. He's mentored high school students, including one at Stanford for a research project. He's mentored undergraduate students, including one who's now doing his PhD. And he's just been all around and available to the group. He also co-founded an organization to help underrepresented undergraduate students understand grad school and how it takes to bring students into Stanford to help teach them about the grad school admissions process and how to go about that. I think actually really cool to see. And I think that's an impact that will last long is kind of. So with that, we're really excited to hear about some of this exciting work that we've done in the last 5 years. And I'll hand it over to Sebastian.
Okay, great. Thank you. Thank you. All right, thank you for the kind introduction, Dan. I want to thank everyone here that's in person as well as on Zoom. And it's my pleasure and honor to tell you about some of my doctoral work, which has looked at alternative emissive perovskites for applications in the visible and ultraviolet spectrum. So the outline for today's defense, we'll be looking at why we should care about this particular material class system and how we can integrate them into devices and how we can do that in an intelligent way. Following into the first story, in which we'll look at how we can use manganese dopants to drive the efficiency of a green perovskite LED platform and the interesting trade-offs that we'll see between the efficiency and stability within this platform as well. Then moving a little bit further into the visible spectrum, we can look at synthesizing a new material class system that is purely lead-free, that can emit at the deep blue and violet ranges. And then very quickly, we'll talk about several stories. The first one very briefly on how we can use 2D lead halide perovskites to enable violet and ultraviolet light-emitting devices, as well as how we can take advantage of thermal evaporation of perovskite materials to really move into this uncharted ultraviolet spectrum territory. And so to begin, one of the most applicable places in which we can integrate LEDs is solid state technology. And so from the Department of Energy, our current solid state lighting path, we're predicted to save around 62 quads of energy by 2035 by using these technologies, in which one quad is approximately 300 billion kilowatt hours. However, pursuing a slightly more aggressive Department of Energy solid state lighting goals, we can save an additional 16 quads of energy through 2035. And in total, this 78 quads of energy that we can avoid is around $900 billion in avoided energy costs, really demonstrating how important it is to innovate at the materials, device, and integration level. On the other side of the coin, we can also look at integrating LEDs within display technologies. So here I'm showing an iPhone 14. I think many of you probably have this phone or a newer one, in which the screen is made up of an OLED or organic LED screen. And so the emitter material that you might find within this technology is something like this ERP organic molecule. Additionally, our smart TVs, such as the Samsung QLED TV, might be made up of emitters such as this indium phosphide, zinc selenide, sulfide core shell structure. And while we've come a very long way, there is still much more we can do to enable next generation displays. But how do we go about quantifying that? So we can introduce what is known as this REC 2020, which is a standard for ultra high definition displays. And we can also look at the red, green, and blue light emitting devices or emitters across various material class systems. So organic, cadmium and cadmium-free quantum dots, perovskite nanoparticles, and polycrystalline perovskites. So to dissect this chart first, we can see that we're plotting against the agreement with this ultra high definition display, where we want to be very well adhered to ensure very high definition displays within our technologies, as well as the full width half maximum, which we want a smaller full width half maximum to ensure that we have as pure, in this case, red light emission, but also pure green and blue light emission as well. So the champion area of this first chart is actually here in the bottom right, where we can see that perovskite materials in general are not only really well adhered with this ultra high definition display standard, but also have very short full width half maximum, ensuring that we have really sharp, pure red light emission. And we see that this story actually holds true for the green and blue emitters as well. We have both across RGB, perovskite materials are very well adhered with REC 2020 and very sharp green, blue, and red light emission. Now, it's not enough at this point to just have great performance. We also must have great performance at low cost. So if we look at things like the actual time that it goes into manufacturing these materials, and as well as their inherent material costs at first, we can see that these perovskite materials are not only very quick comparatively to manufacture, but they're also very low cost. And finally, by looking at their agreement with REC 2020 in general, we can see that it's very well adhered. And from the CIE triangle, we can see that perovskite LED technologies have the potential to really span the standard and enable very inexpensive and next generation displays. So what makes these materials quite interesting? We can look at the crystalline structure of these lead halide perovskites, in which here it is governed by an ABX3 structure, in where A is an organic or inorganic cation, B in this case is lead, and X is a halide anion. From the picture on the right, we can see that we can sweep across the visible spectrum based on the halides that we choose, as well as from the picture on the top, we can see that these materials are solution processable, implying that they're very inexpensive and easy to produce. And so in the aggregate, these together really suggest that these lead halide perovskites are candidates for next generation light emission because of these inherent really fantastic material properties. However, there is a problem here, and that is that we have lead within these materials. Now, some of you may remember the amount of toxicity and health problems that are related to lead paint. And in fact, in my hometown of Georgia, there's actually still a law firm looking at the various amounts of health issues that occur from living or in interacting with buildings that have lead paint within them. And so if we think about it, if we want to integrate these technologies and they have lead, if we look at integrating them into like our smartwatch, and as we're playing with our smartwatch, if the encapsulation fails, we run into this issue of we could harm ourselves. This is a very serious problem for public health. And so the overall guiding question that guides my doctoral research here is, how can we mitigate these toxicity concerns, both within materials and integrating them into devices, and really engineering at this B site to mitigate the amount of lead that we have in these emissive materials. And so that brings us to the first section, in which the Congreve Lab in the Rowland Institute at Harvard first looked at what if we replace a certain percentage of the lead with manganese. And what they saw was that across green, red, and sky blue thin films, up to a 30% replacement of manganese dopants actually improves both the brightness and the uniformity of the thin film. Encouraged by these results, the workers then looked at integrating them into a device. And for reasons that will become obvious soon, we'll focus on the green light emitting devices. in which here we have the external quantum efficiency versus the current density. So the external quantum efficiency of a device for an LED is defined as the ratio of the number of photons that are emitted from the device, the number of injected carriers within the device itself. So you can think of a general figure of merit of the efficiency of the device in general, in which they saw we can monotonically increase the EQE to a new record of 3.2% for this manganese dope LED platform. For the stability, we can look at the evolution of the luminance, which is related to the amount of photons being emitted from the device. And so with a device that has no manganese dopants, the stability is less than 1 minute, but afterwards it is, with 30% manganese dopants, it is increased to 23 minutes, really showing that in the aggregate, all of this together shows that we can at first increase the uniformity and brightness of these hybrid organic-inorganic perovskites with manganese dopants. But also this translates into great gains in both the external quantum efficiency and the stability of the devices together. And this was a fantastic first step, but unfortunately these external quantum efficiency numbers and the stability are not as high as they need to be in order to enable this lighting technology. And the primary reason for this is there is still a high density of surface defect states that are reducing the amount of radiative recombination that can occur within these thin films. And so recently there's been a new additive class system known as phosphine oxide additives, in which basically what I want you to focus on here is that the phosphine oxide moiety can actually coordinate with the lead site within the perovskite, which in general can passivate and reduce the amount of surface defect states and enhance the radiative recombination relatively within the perovskite thin film, really driving the emissivity of that thin film and hopefully leading to better performing devices. Additionally, it's also known within perovskite PV to suppress electron recombination, really showing the strength of this additive class system, both within light emitting technologies and light absorbing technologies as well. And so that brings us to the first story today, in which we look at pairing a phosphine oxide additive with the manganese dope perovskite LED platform. So here I'm showing trifluorofluorophenyl phosphine oxide, TFPPO, and we're able to introduce this to the perovskite material via the chloroform anti-solvent. So we focus on concentrations of 0, 5, 10, and 20 milligrams of TFPPO per milliliter of chloroform anti-solvent that is solution processed within this thin film. And we can see that we can improve the photoluminescence quantum yield, which here is defined as the number of photons being emitted from the thin film to the number of photons that are actually absorbed by the thin film as well. And so we're reaching PLQIs of around 67%, which are over 2x of the 2019 value. And from the picture down below, we can also see the stoichiometry of the hybrid quasi-2D, 3D perovskite that we've created. But under UV light, we can see in general that the emissivity of the thin film is increasing with TFPPO concentration. Also looking at the atomic force microscopy images, we can see in general a change in the morphology of the thin film. And nevertheless, we look at then integrating these thin films into LED devices. So to skip a lot of the really hard work that went into optimizing the device up to here, I'll briefly highlight just 2 key differences from the 2019 device. So the first one is including this insulating 1.5 nanometer lithium fluoride underlayer. And the reason for this is twofold. The first one is to reduce the amount of exciton quenching that would occur between the perovskite and the P.PSS PFI whole transport layer. But also because these materials are solution processed, the P.PSS PFI layer is known to be very hydrophobic. And so by adding a lithium fluoride underlayer, we can improve the wettability of the perovskite in general, really ensuring that we have a nice deposition of the active layer itself. Lastly, we also use a more non-traditional electron transport layer through TPYMB because we want to facilitate the electron injection from the lithium fluoride aluminum electrodes, and it's very well aligned with the conduction band minimum of the perovskite active layer. So in general, we can then see across the TFPPO concentrations that we looked at, there is no clear red or blue shift, so no increase or decrease in the wavelength emission from these materials and devices. And it's fairly well centered at 520 nanometers. Within the inset, we can see a very bright green, pure LED. Now, focusing on the champion efficiency devices within this study, we saw that all these devices have a turn-on voltage of around 2 to 3 volts, which is really quite good because it implies that it's a very well-engineered device because we're very close to the optical band gap of the perovskite active material, as well as reaching maximum luminances of around 100,000 candela per meter squared. Now, while not shown here, within the study, we also measured champion brightness devices, which were as high as 128,000 candela per meter squared, which were at the time one of the highest among the reported perovskite LED literature. If we now look at, again, the figure of merit, EQE, for device efficiency, we can see that with TFPPO concentration, we can monotonically increase the EQE to a new record of 14.0%. And in order to ensure the validity of these claims, we can also look at the device statistics. And across 120 devices, we can see an overall 5x improvement in the EQE, which makes us confident to say that we're definitively improving the efficiency of these devices by using TFPPO. Now, this is overall a really promising and great story thus far, but if we really want to enable new kinds of lighting technologies, we also have to consider both efficiency and stability hand in hand to really look at the various trade-offs that might occur and how we can make this technology more of a possibility. So that's where we focus our efforts next. So this is the luminance decay of the perovskite LEDs, so the figure of merit for the stability. And we can see that there are several half-lifetimes that we can extract, which I'll briefly define here. So the first one is the T50 time, which is just defined as the time that it takes for the device to reach half of its initial luminance, which for this violet curve is annotated with this violet circle. But you'll also notice from this violet curve that we actually achieve a luminance much higher than the one at t equals 0. And so in order to fairly compare, we also define an adjusted T50 prime time, which takes into account when we actually reach that maximum luminance, and then we look at half of that value to actually calculate the half-lifetime in that case. And so if we extract the T50 and the adjusted T50 prime lifetimes across TFPPO concentration, the trend is actually the same. And that is, as we increase TFPPO concentration, we actually see a reduction in the stability within these devices. And again, across device statistics, we can say that definitively this is not a one-off case. This is actually truly happening within this platform. And so now pitting together the device efficiency characteristics of the champion efficiency devices and the adjusted T50 prime or the half lifetimes of the champion stability devices, we see this interesting efficiency stability trade-off start to emerge. And unfortunately, we see that, yes, TFPPO can improve the efficiency of these devices, but however, it also impairs its stability. Now, within the perovskite LED literature, this is quite rare. Usually when you have an improvement in efficiency, you either see a net neutral or net positive improvement in stability as well. So to really dig at this further, we look at conducting repeat electrical scanning measurements, as well as time-resolved photoluminescence decay measurements as well. So first, looking at the repeated electrical scanning measurements, I'll briefly define what this measurement setup is here, in which the electrical scan is a current density voltage luminance scan. We take it for a fresh device at time equals 0. Then we stress the device for 2 minutes at 10 milliamps per centimeter squared, followed by another scan, followed by 4 minutes of operation, followed by another scan. And graphically, this can be shown here as to how we can get 30 minutes of total operation at 10 milliamps per centimeter squared, equating to 5 scans that we can take from these devices. And so there are various optoelectronic parameters that we can now start to probe under identical operating conditions. And we can look at them together across TFPPO concentration. So the first one I'd like to focus on is the evolution of the turn-on voltage, which is defined as the voltage when the device reaches a luminance of 1 candela per meter squared. And what we can see here generally is that the devices that have TFPPO have a much stronger degradation in the turn-on voltage, which implies that the injected carriers in the device see a much harsher obstacle to recombination that leads to light emission within the device itself. If we look at the operational luminance, which is the luminance of the device at 10 milliamps per centimeter squared, we can see that the non-TFPPO treated device starts at a lower luminance, but does sustain that luminance for a little bit longer, and at time equals 30 is actually the more efficient device as compared to the 5 and 10 meg per mil device. And I would argue if we extended this measurement out even further, it might become more efficient than the 20 meg per mil device as well. And lastly, if we look at the evolution of the maximum luminance of these devices, we can see that in general, the ones with lower TFPPO concentration might start off at a lower maximum luminance, but are overall a little bit more robust, showing their integrity and applicability for high brightness applications such as laser diodes. And so by putting all of these together, what we can say here is that the TFPPO treatment might initially improve the LED performance, but however, the optoelectronic parameters do degrade with operation, really suggesting how TFPPO is influencing the optoelectronic parameters within the device itself. Now looking at the time-resolved photoluminescence decay, the measurement setup here is that we take a fresh device, measure its photoluminescence decay, followed by 1 hour at 10 milliamps per centimeter squared of identical electrical operating conditions, followed by another scan. And we can see that all of these measurements can be modeled by this bi-exponential decay model, in which the lifetimes here, tau1 is a faster non-radiated recombination that is more associated with the grain boundaries within the perovskite thin film, while tau2 is a longer, more emissive, more related to radiated recombination pathway. Additionally, we can also define an average of these two lifetimes, so both with their contribution of A over A plus B and the tau 1 and tau 2 accordingly. And by annotating these tau averages together, we can see that in general, with higher TFPBO concentration, we see a greater reduction in the tau average. And this is largely due to both the contribution to tau 2, which is B over A plus B, as well as a reduction in the tau 2 lifetime, which is related to the emissive and radiative recombination nature of the perovskite thin film. Also looking at the photoluminescence quantum yield, both before and after the degradation of these devices, you can see a clear monotonic decrease under identical electrical operating conditions, which together paired with the time resolved luminescence decay measurements allow us to say that the overall emissive efficiency of these devices is decreasing, typically with higher TFPBO concentration. And so in general, we've shown that we can improve the efficiency of these thin films with this TFPBO or phosphine oxide additive system, but it unfortunately does come at a great cost and stability, nearly 15-fold. And so where to move to next from here is how can we keep these efficiency boosting properties from the phosphine oxide additive class system while mitigating the stability impairment and really understanding the interactions with the materials and how they integrate into the devices altogether. Okay, great. So now we'll move towards a little bit further into the visible spectrum, looking at deep blue and violet light emission based on a purely lead-free platform. And before we get to that, I want to quickly derive how we get to perovskite nanoplatelets from this bulk structure that I showed previously in the introduction. So again, I'm showing the same ABX3 perovskite structure, only this time I'm briefly highlighting the unit cell, which will become more important very quickly. And we can start to introduce these ligand species in which the authors use oxammonium and butylammonium here. And when we introduce these to the synthesis of this material, we can actually start to confine the growth of the material to lead to something that looks like this. So confining their growth in one direction, and therefore leading to formulas that look as follows, where L is again the ligand species, ABX3 is this bulk unit cell, and this N-1 is the thickness of the platelet in terms of that unit cell. So here we can see clearly that we don't have this unit cell within that first structure. And so this is actually the N=1 perovskite nanoplatelet governed by the formula L2BX4. However, if we start to have one unit cell, this would be the N=2 perovskite nanoplatelet. And we can keep going with this, but this will largely limit the discussion for this section here. Okay, so how do we go about synthesizing these perovskite nanoplatelets? So in general, we can dissolve these precursors, so the ligand species, the metal species, and the A-site bulk cation species in a polar solvent such as DMF. We combine them in a proper ratio to create the particular perovskite nanoplatelet that we want to synthesize. And then by dropwise adding these precursors to a crystallization solvent, in this case, the authors use toluene, under vigorous stirring, we can actually see the instantaneous platelet formation. So in theory, to make the N=1 nanoplatelets, we would combine the ligand, metal, and A-site cation in a 2:1:0 ratio, so no bulk cation. In theory, to get the formula that we want for the N=2 nanoplatelets, we would do a 2:2:1 ratio in this case, but the authors found that we actually need a little bit more ligand, so a 10:2:1 ratio, to prevent the growth of any thicker nanoplatelets, so those between N=3 and N=infinity, and ensure that only N=2 nanoplatelets would form. And so the way that this looks is that we have the solvent that is stirring, and once we drop the perovskite nanoplatelets, we can see the formation of these materials immediately. And so now if we look at the optical properties of these materials, we can take these point by point of how they vary by metal, halide, and thickness. So the metals here are tin and lead. So first focusing on this pair of absorption and photoluminescence spectrum, and this one here, we can see that the tin-based systems are overall redshifted or in lower energy as compared to their lead counterparts. Across halide, if we compare the lead from iodide to bromide to chloride, as we move from iodide to bromide to chloride, we can see a general blue shift or higher increase in the energy of the photoluminescence and absorption spectrum here. And lastly, across thickness, and perhaps one that I'll take some time to briefly explain, is that for any one of these metal halide pairs, if we compare the N=2 to the N=1 case, the N=1 is always at a much higher energy and is more blue shift than N=2. And this should make sense from quantum mechanics. We know that quantum confinement effects will increase the optical band gap of these materials. And so for every one of these cases, the more thinner nanoplatelet will have a higher emission. The authors also looked at what we can look at across mixed halide. And we can see these beautiful transitions in the absorption spectrum for both N=1 and N=2 nanoplatelets. And so where do we move on from here? Well, we can see that the tin-based system offers a lead-free and hopefully reduced toxicity or toxicity-free platform for these materials. And from my own previous work and those before me from the concrete group, it's been shown that there's a pathway to use manganese dopants and hopefully a full manganese platform at some point to reduce the amount of toxicity for the green, red, and sky blue regimes of the visible spectrum. But we're missing a solution here at the deep blue and violet range. And if we're really going to think about how we can integrate these technologies further, we need to consider alternative lead-free technologies. And so here, in conjunction with Divine Batu, who's within the group, we can play the same trick. We can have our crystallization solvent, which is stirring, and drop our europium-based halides, so purely lead-free, to create these deep blue and violet light-emitting perovskite nanoplatelets. So in this case, the ligand species is phenethylammonium, which is annotated here. And in general, we can see that the pure bromide-based materials will emit at the deep blue of around 450 nanometer, while the pure chloride-based system will emit at around 430 nanometer, which is now in the violet regime. We can also look at forming these nanoplatelets across various ligand species. So here we have N-butyl ammonium and defluorinated phenethylammonium, and also mixing them with one another. And in this case, we see not too much tunability, which makes sense because we have, in theory, the same kind of thickness within the nanoplatelets themselves, really showing that this is a new material that can really emit in the deep blue and violet ranges across organic space or cation. But we're missing something. We're missing the thickness, right? So what about the N=2 case? So I'll briefly, again, in case you forgot from maybe 60 seconds ago, the N=2 case will always should be in theory at a higher energy or lower energy case than the N=1 because of the reduced quantum confinement effects. And so here we're going to look at how we can create these nanoplatelets. So again, by looking at the previously reported 2:1:0 ratio, we should get the N=1 nanoplatelet, which is starting at a photoluminescence peak at around 450 nanometers. And then when we look at the 10:2:1 ratio, from this system, we should see some sort of redshift. But we don't see that here due to reduced quantum confinement effects. If we look at expanding further, adding even more bulk cation, we see that this bulk methylammonium bromide doesn't shift the photoluminescence at all to the system. And so curious to understand why, we then looked at conducting X-ray diffraction or XRD measurements as well. So from the previous study, this is a typical XRD scan or a 2D perovskite, which has a periodic nature, and the diffraction peaks are aligned with the 00L lattice plane within the structure itself. And for the N=2 nanoplatelets, we can see a slight distortion within that 2D structure. And within these black circles here, we can see some peaks that are reminiscent of the unit cell that we would be creating within these nanoplatelets in general. And so again, the ligand species here is octammonium and butyl ammonium. And so when we looked at centrifuging out our nanoplatelets and characterizing them at XRD, we first see that this typical 2:1 ratio is not reminiscent of this 2D perovskite. And our hypothesis here is likely that there is an underreaction between both the phenethylammonium bromide and europium bromide precursors. But when we look at conducting the XRD of the 10:2:1, which should in theory be the N=2 nanoplatelets, we start to see the periodic nature of the XRD scans, which are very reminiscent of the scan up here. And in fact, if we look at them with increased methylammonium bromide, we don't really start to see XRD scans that resemble that of the N=2 case here, which is really showing an interesting deviation from the previous class system that we've seen down here. So then the theory here is that the methylammonium bromide is not really contributing to the crystalline structure of this material. And so at this point, nice. We look at forgoing the bulk A cation completely. So this 10:2 ratio of phenethylammonium bromide to europium bromide, which we have this scan of the most representative XRD scan that we can have. Now, the theory here, we can't directly compare with the previous authors because not only do they have a change in the metal, so from europium to lead, but they also have a change in the organic spacer cation. And we want to make as close to a comparison as possible. So the most likely candidate in our hypothesis is that hopefully the structure is very similar to something like phenethylammonium lead bromide. So just an alternative metal case basis. And luckily we didn't have to go too far because my colleague Manchen was able to characterize the XRD of these 2D perovskite nanoplatelets. And we can see some striking similarities. So the first one being that the periodicity between the diffraction peaks is really quite similar, implying that these nanoplatelets have really similar stacking distances, which should make sense because we have identical ligand species in this case. And when we start to annotate the diffraction peaks from here, we can see that in general, this europium-based material is right-shifted for all of the peaks as compared to the material up top. And this is in really good agreement with previous reports of the ionic radii of europium and lead together, where europium is known to have an ionic radius that is a little bit smaller than lead. And so this starts to suggest to us that we're actually forming phenethylammonium europium bromide together because it is quite similar to the phenethylammonium lead bromide. We just take the lead and replace it with europium in general. You can also look at imaging these materials. So here we were able to find a report of a single imaging of a nanoplatelet based on a fluorinated phenethylammonium lead iodide nanoplatelet. And from our SCM images, which were done with Hans Wei from Guosong Hong's lab, we can see that we hope that we're forming the perovskite nanoplatelet itself. Of course, we're missing some additional information, such as EDS, which is currently still in play. But in general, what I want to say here is that there are some size differences here, which are largely attributed to the changes in crystallization from the material. But in general, we're seeing a very similar shape and along a very similar lateral size, which is really indicative that we are forming what we think we are forming. And at this point, I'll refer to this as the excess ligand. So having more than the previously reported 2-to-1 ratio, this is now a 10-to-2 ratio of ligand to europium bromide. And so now let's look a little bit more at the optical properties of these nanoplatelets. So something that we want to mention here is that both for the tin and lead-based system, the absorption and the photoluminescence, as demarcated by the dotted lines and the solid lines, are pretty on top of one another. And this was something that we were not seeing with this Europium-based system, which confused us and suggested that maybe we're not forming what we think we're forming. But we can go no farther than actually UC Berkeley within Peidong Yang's group and see that they've created cesium europium chloride-based nanocrystals that have this strong excitonic absorption around 350 nanometers. However, their nanocrystals in this case emit at around 435 nanometers. But because there's really good adherence between the photoluminescence excitation and the absorption spectrum here, the light emission is confirmed to be originating from the absorption of these nanocrystals, no matter how far the various absorption peak and the photoluminescence peak might be. Additionally, from these materials, again, for those that work within the space, we know that nanocrystals are a little bit more difficult to synthesize than the more simpler nanoplatelet synthesis that we've shown previously within here. They were able to achieve PLQIs on the order of 2 to 5.7% with additional treatments. And so this kind of guides the rest of the section here. So again, these are the N=1 under-reacted 2-to-1 ratio that in theory should be these materials. And we can see that we have a very similar case here where we have the strong absorption peak at around 350 nanometers, and that we have really good adherence between the photoluminescence excitation and the absorption itself with the photoluminescence that has already been shown. And for these materials in the solution state, we have PLQIs of around 0.5% and 2.25% for the chloride and bromide respectively. But what if we look at the solution state for the optimized, the true N=1 nanoplatelets across various ligands as shown here? We can see that the absorption is still quite the same. We have the peak at around 350 nanometers, good adherence with the photoluminescence excitation and the PL. And this time we're able to achieve PLQIs as high as around 11.6%. And just as a brief note, when we drop cast them and centrifuge out these nanoplatelets, these excess ligands, the picture doesn't do justice, but it's really bright, dark blue, has a PLQI of around 10.8%, really showcasing the ease of how we can create these materials and hopefully integrate them into devices and finish the current material characterization that we're looking at. Okay, and so now for the final section here, we'll look at how we can engineer wide bandgap perovskites and really move towards the ultraviolet light spectrum. So why should we care about the spectrum regime? Well, Manchin did a really nice job of summarizing this here, in which hopefully earlier on in the talk, I've motivated why lighting and display is really important for visible spectrum, but there's also really interesting applications for the ultraviolet spectrum as well. So first and foremost, as clearly demarcated from the recent pandemic, those related to public health. And so being able to make impact within water purification and sterilization applications is really, really important, as well as those related to 3D printing, nanofab, and sensing are also equally important. And so how do we get there? It seems that we're kind of limited to the visible spectrum. Even if we use like a pure chloride-based system, it's really hard to move into the ultraviolet spectrum. With my time within electrical engineering, just in general, from undergrad to my PhD, has taught me that a lot of the answers can actually lie in the past. So if we look at something like a 3,5 LED here, we can focus on this indium, aluminum, gallium nitride quantum well structure, in which by using quantum wells, we're able to artificially increase the optical band gap of the material by confining the states within the material itself. And it turns out we can play the same trick here. So we've already kind of looked at this material, but in general, we can quantum confine this lead bromide octahedra between these organic phenethylammonium layers, creating the same quantum well structure. And this will briefly show some of the work that was done within this group towards moving towards the ultraviolet spectrum. And so from here, majority led by Manchin, we looked at how we can use this phenethylammonium lead bromide layer, which hopefully many of you were at Manchin's defense a few weeks ago, in which we can yield 408 nanometer violet light emitting devices with an efficiency of around 0.41%. By exchanging just a little bit of the bromide with chloride within the system, we can also push towards the ultraviolet spectrum by having a 9 nanometer blue shift and showcasing the first ultraviolet light emission from these lead halide perovskite materials. But I also want to say that working in this regime has a lot of difficulties, as many people in the field will tell you, because in order to now have transport layers that can actually facilitate the injection of electrons or holes within the material that can achieve band gaps as high as this is really, really quite difficult, and will also guide some of the discussion that's to come. And so how do we move from there? So after the demonstration of the chloride 1 bromide 3 structure, Manchin and I actually did take a little bit of time to see if we can push that even further. Can we exchange more of the bromide with chloride? And we start to run into solubility issues. And we also want to think about new material class systems to move deeper and take a more dramatic step into the ultraviolet spectrum that can really facilitate the impact of this technology. And so recently there's been reports of lanthanide double perovskite nanocrystals, which can showcase light emission from the deep UVC based on the praseodymium-based materials all the way to the near infrared spectrum based on the Europium-based materials. Now here I'll briefly highlight the cerium-based perovskite, which thanks to this D to F electronic transitions within the material has this doublet emission. You can kind of see two peaks here in the photoluminescence that are thanks to the transitions here. So a peak at 370 and 410 nanometers. And so while this was shown in the solution state, it's really important to think about, could we implement materials such as these in perovskite thin film? And if we can, how can we do so? So these materials also have difficulty with solubility, and we also need to consider new deposition techniques to really push this technology forward, such as thermal evaporation, both for perovskite LEDs and emissive perovskite materials in general. So how this works is we can load those same perovskite precursors into this crucible, pump the chamber down under vacuum, evaporate them by applying a lot of heat within the crucibles. These gaseous molecules will interact within the chamber, leaving behind a solvent-free perovskite active layer. And now there may seem a lot of advantages with this type of deposition technique as opposed to solution processing, such as, first and foremost, this technology is already pretty industrially compatible. This is used to make some of the organic LEDs that we use today, as well as we have very large device area capability. We're not limited by the centrifugal force in which we're spin coating. And lastly, we can reduce the device-to-device variability that is largely seen within spin coating. And so why has there been such a key push within spin coating, within perovskite LEDs and perovskite PV in general as well? And actually, it can be explained quite succinctly with this chart here, in which, unfortunately, we just don't have the amount of tricks and things that we can do within thermal evaporation that we can do within spin-coated perovskites, such as those related to additives and crystallization. But given the other pros here related to industry compatibility, device areas, and reproducibility, I do believe that this is likely the path forward if we really want to commercialize these technologies further. And so additionally, now looking at the thermal evaporation of these rare earth element-based systems, previously workers had shown that by thermally evaporating cesium bromide and europium bromide together, it can lead to these deep blue thin films, which emit at around 448 nanometers. And by integrating these perovskite thin films, the authors were able to land on this structure, which is a little bit different from the other structures that I've shown thus far, in which the perovskite layer is actually sandwiched between two insulating lithium chloride layers. And this is because the perovskite layer itself wants to, oh, sorry. That is not content. I'll quickly end the show. And then do this again. Nice, okay. And so, yeah, by sandwiching the perovskite layer with these lithium fluoride underlayers as well, it's in order to avoid the amount of leakage current that might occur from the cesium europium bromide thin film. And then the authors showed that by simply tuning the thickness of these lithium fluoride layers, they were able to tune the device performance and eventually lead to a maximum external quantum efficiency of around 6.5% for this pure lead-free platform. So encouraged by this, encouraged by the results from the lanthanide double perovskite class system, and because I was responsible for a lot of setting up the perovskite thermal evaporator within the lab, we then looked at thermally evaporating this cerium-based system first in this dual source evaporation scheme as shown here. And so by carefully tuning the rates and the ratios of these materials with respect to one another, we're able to then, from the photoluminescence of this material, take a dramatic step forward into the ultraviolet spectrum by now having a peak at around 367 nanometers with a shoulder at 400 nanometers. Now taking very dramatic step now into the UVA spectrum and seeing what we can do from here. So now looking at the optical properties of these perovskites, we can look at characterizing the absorption and the photoluminescence excitation of these thin films. And accordingly, as was shown in the perovskite nanoplatelet section, there's good adherence between the absorption and PLE peaks centered at around 325 nanometers. And additionally, now we can introduce cesium bromide and do this tri-source thermal evaporation, in which let's see what happens if we use halide engineering. Can we affect the optical properties of these thin films? And it turns out as we move from a pure chloride to a mixed bromide chloride, we get, as we expect, a redshift in the absorption peak from 324 to 330 nanometers. And as well as we can see more clearly within the sunset here, as well as similar trends within the photoluminescence excitation spectrum, we can also see from the photoluminescence of the thin film that we can move from 367 to 384 nanometers, really showing the tunability from using the cerium chloride-based precursor. But we can play the same trick. We can try to evaporate cerium bromide-based precursors as well, and now showing the redshift or the blue shift that was as we had more cesium chloride to the system, and we move from bromide 4 to this mixed bromide chloride. We can really see that putting these two materials together, the pure bromide system has its primary peak at around 390 nanometers. So showing this general tunability across 367 to 390 nanometers, again, shows the clear halide engineering that we can enable from these UV-emitting cerium-based perovskites. Lastly, because we're limited in what we can do within the perovskite thermal evaporator, another knob is by looking at the in situ annealing temperature. So that is the temperature that we can apply on the substrates themselves as they're being evaporated on. And so the authors from the cesium europium bromide work showed that from moving from a low room temperature to a higher 200 degrees Celsius temperature, when the photoluminescence, we can see the decrease in the full width half maximum, which is important for the display application for these LED technologies. And as well as from the XRD, you can see a greater increase of the crystallinity between the cesium bromide and cesium europium bromide as moving to higher in situ annealing temperatures. So we have a similar capability within our lab in which we first, again, we've already shown the pure chloride-based system at room temperature, but then moving to a lower temperature of minus 10 degrees Celsius, we start to see very similar, this singular broad peak, which again is similar to the previous reports, implying that maybe there was an underreaction between cesium chloride and cerium chloride. And at the time, we're limited to 100 degrees Celsius. We've been able to move that slightly, but we can see that there's not too much of a difference between the 26 degrees Celsius and 100 degrees Celsius. But it's hypothesized that as we move further, perhaps we can further impact the photoluminescence spectrum of this material. But in general, showing that the substrate temperature can really influence the optical properties of the cerium-based perovskite. And so from here, we're doing additional materials characterization, as well as we initially explored for just the pure chloride system LED integration, which was really quite difficult given the difficulty in the film morphology. But now for the pure bromide-based system, we can look at potentially working at that within those materials as well. And so to briefly conclude, we looked at how we can improve the efficiency of these perovskite LEDs with manganese dopants, but unfortunately comes at a cost of stability using these phosphine oxides. How these europium-based pure lead-free perovskite nanoplatelets offer lead-free deep blue and violet light emission, and additionally how 2D emissive perovskites can enable violet and ultraviolet LEDs, and how the thermal evaporation of cerium-based perovskites can really move us more forward into the ultraviolet spectrum. And so with that, I'll briefly flash journal publications and then say brief acknowledgments just of thank you. We'll do the more full thing afterwards, and this concludes kind of my section of this talk. Thank you. Yeah, that's a good question. Yeah, so there has been, I've seen recent reports, not necessarily focusing on like our specific hybrid organic and organic quasi 2D, 3D structure that like both myself and Mahesh have kind of looked at optimizing. But in general, what I found within my platform, and I think Mahesh also found within his platform, was that it was kind of a Goldilocks thing. As when we saw up to a 30% replacement, we can see a net improvement in the device and the thin film. But as we start to push more and more, we start to get this characteristic orange emission from the manganese dopant itself, which is kind of altering the perovskite structure that we're looking at. But there have been other reports. There's potentially other synthesis things that we can look at doing. But for now, that was kind of the optimized manganese dopant replacement that both myself and Mahesh saw. Yeah. Yeah, absolutely. I think for the phosphine oxide based system, what would be really applicable as well is seeing the interaction between the various components within the perovskite itself. So I think it's fairly well understood that the phosphate oxide moiety will coordinate with the lead side, but we don't necessarily understand its effects with the A side cations or with the halide anions as well as across various dimensionalities and other sorts of modalities on how we can create these materials in general. So I think if I were to relook at this and start to expand forward, what I would look at is both looking at TFPPO, but also other phosphine oxides such as TPPO or TOPO, and integrating them within the thin films to see if we can see a similar trend in efficiency and stability across many types of perovskite LED platforms, and start to understand what exactly is going on in their interaction with the materials in general. Yeah, I mean the cesium europium bromide based work has shown that there is like some tilting that occurs with the octahedron based on the europium based system, that we're not getting as kind of a clear cubic kind of unit cell that we see typically with lead or tin, which also implies that it's like a quasi perovskite like material, but not exactly so. But yeah, so this is in general what we saw from the thermal evaporation, and also within the europium based system for nanoplatelets as well. But yeah, the hybridization as well of these states is something that people are still also additionally kind of looking at. But yeah, in general, it has been shown that the structure is really quite similar, but has a little bit of differences that we can't, I guess, fully. If I go back to like my slide 3 or something, it's not exactly that crystalline structure. If that makes sense. Sounds good. Is there anything on Zoom? Okay, nice. Yeah, thank you. So I guess I'll do some brief acknowledgments, and then either Tomas or Dan will kick everyone out. So I think, as I mentioned, a lot of the extra stuff that I've done at Stanford has been equally, if not more important, I think, because people, I think, in general, to me, are more important than the actual science that I'm doing at any given time. And so I've had the pleasure of, co-founding the Stanford Engineering Research Introductions Organization, and I've served as president for the past 3 years. And some of the students are even here today. So if you look at really young students in the room, don't think that grad students are getting really, really young. They're just really, really excited about research and are here to support me today. And so what we were interested in within the organization is, at our core, we want to really support these underrepresented students and their pursuit towards graduate school. And in fact, we have our 3 major tools of success on how we can support them, which is largely current graduate student mentorship with the Stanford graduate student here, as well as maybe quite the most important is a healthy early exposure to research to really improve their taste in research as well as their maturity and hopefully become more viable graduate school applicants, as well as the connections with faculty members, not only for the letters of recommendation, but also encouraging various opportunities for them throughout their undergraduate career. And we largely do this initially through our 3-day conference-style program at Ceres, where we use things such as seminars, workshops, lab tours, grad student panels, and faculty presentations. Feel free to talk to Iman or Debbie afterwards to see how impactful that's actually been. But we've started to see really, really key results here. And so just to briefly highlight some of the success stories, we've seen students, and I promise there's more that I could show, but I'm limited on time, is that we have both Nyla and Chase here, who were freshman students getting involved in research as early as their freshman year, followed by Francis and Peter, who have gone as far as publicly presenting their research in poster presentations, publishing their research in journals and conference papers, as well as presenting their research at an APS meeting as a junior and undergrad, which is really, really quite exciting and inspirational. And additionally, we've been able to create this really nice loop now that we've been around for some time. So the goal was always to support these undergrads, get them into research, and hopefully eventually publish and present their research as well. And now we actually have a few success stories. Again, we have more, but it's just what can fit on this slide, in which we have Diana and Bianca, who have received admission offers from Stanford and MIT for their PhD program, who we knew as an organization since their freshman year. And in fact, Diana will be joining us here at Stanford CS PhD very soon. And she's communicated that she wants to get involved with Sarah as a graduate student, really repopulating and showing the strength of the efforts that we've had thus far. And so in general, just the 2 slide of our impact is we've had nearly 90 students participate in our 3-day Ceres-style program, as well as matching all of those students plus additional Stanford students and the students from other universities with mentors from the SOE and other disciplines within Stanford as well. And none of this would have been possible without the very fierce support that we've had at Serio, and those that have served on the e-board. So Claire, Aaron, Chandler, Sarah, Austin, Chloe, Linda, Ilana, Frankie, Kanish, Camilla, and Hubert have all played a really significant role. And I'm quite proud of where we're leading things and how things will go from here on. Okay, yeah, then first looking at Dan, I think I really have to give my flowers here because, as Dan had mentioned, we had joined at a very interesting time in which we had to wear masks and stand 6 feet apart. So I think this was actually one of the first group pictures that we ever took, which was an interesting way to get to know the group. But the group has started to form a really interesting dynamic and has been very inclusive for everyone involved. And a lot of that is due to who Dan is as an educator and mentor, and we really appreciate that about him. As well as Dan puts his money where his mouth is, and he gives up a lot of his time to mentor underrepresented students and give his time to really dedicate and show students what is possible with their engineering education. And lastly, he's always shown up for me, both professionally and personally, and I'm very proud to be a student and to be graduating here today, or later on, but hopefully passing today. Yeah, so then I have to thank Tomas Jaramillo, who's my chair, and I had to really, really make it work so that he's here today because he's also a very important person to me because he's also my DARE mentor and has always been there and stepped up, and I've admired him for quite a long time just because there's not that many Hispanic faculty members, and so those that can relate to some of the issues that I might have to incur is really important to me, and so I thank you a lot for all the advice that you've given me throughout this time. Also thanking all my committee members who have shown up on in quals committees, in DARPA scope meetings, and in various lunches who have given support and given me a lot to think about throughout these years. So thank you all for being here. I also want to briefly talk about the communities that make up the various fellowships that have funded my PhD. So before coming to Stanford, I had the opportunity to intern at Lam Research, in which I had my boss, Johan, and a very close mentor in Lindsay. And they were really important into getting me adjusted to the kind of research that I would be doing, but also in general, just introducing me to the Bay Area, because I came a summer before where there was not that many graduate students here within my own cohort. So you can see Johan with his swaggy jacket at a bar that we were hanging out at. And so I'm really thankful for a lot of the time that he spent with me, that he definitely did not need to, but it was just out of the kindness of his heart. So within the VPGE, it was also funded by the SGF Fellowship, which may not have particular coordinators in and of itself. But I do have to thank Manas, Maya, and Katie, who were within my cohort, who also received the fellowship, and we took all our coursework together and are on Zoom and are really, really important to who I am and who I've become throughout these years. From the Department of Energy, the iBuild Fellowship is really important. So I have to thank Amir, James, Moody, and Jason for not only the impactful fellowship that they've created for me and other fellows, but also the community that we've built. Here we got all the fellows and a lot of the DOE related people at Oak Ridge National Lab to really look at the important problems within energy and how we can move forward. And lastly, the DARE Fellowship from Anika, Lanka, Chris, and Ali, who have done a really good job. And some of the DARE fellows are here today and are really beautiful people that have really shown me what and made me hopeful for the future of engineering academia. Alrighty, yeah, so these have been the members that have known me for quite a long time within the group. So first I have to thank Manchan for a lot of the time that he spent on, us kind of co-leading the perovskite light emission subgroup and looking at the various problems that we've looked at throughout the years, as well as both advice professionally and personally that we've exchanged throughout our time. Purnima for increasing my literacy in chemistry throughout time, as well as being a really fundamental optics person and whose paper was published today. So that's super cool. Congratulations. And whose mentorship is really inspiring to everyone in the group. And so I think that's really important to share here. For Aaron, we've always, had to build up a lot of the setups very early on. And that was some of the first initial wins that we've had. And it was really, really important to do that with you. And I really thank you for all the time that you did, as well as all the efforts that you put into this area. And all the students really appreciate you as well. To Dr. Tracy Schlamer, a postdoc that we've known for quite some time. And as Manchan kind of stated, was kind of our lab mom. And has been a really, really key role model to show us how to do research and how to interact with people. And I've been the personal beneficiary of this, of whenever I go to conferences and I just tell people I know Tracy, they automatically think I'm a good person. So I think that's been really, really useful. And lastly, Chi, who came to us first as a master's student, but she was so good, we kept her as a PhD student within the group, and has been really, really useful in looking at, because she comes from a material science background, I'm looking at the materials questions that I've had within the group, and as well as exchanging various tips on how to raise our dogs, respectively. Yeah. So yes, I also have to give flowers to my mentees. So here's Will Michaels, who graduated from this department a few years back, and is currently, pursuing his PhD at MIT ECS, doing much better than I was as a first year for sure. And he's doing absolutely fantastic things. I also have to thank Divine Mbachu and Tyler Kohlenbrander, who are here today, who are first year students that really stepped up in a big way, given the Divine coming from Nigeria and Tyler not really having too much of an experimental background. I think it made a lot of sense for me to also mentor them in some of the projects that I've been working on within the group. And lastly, my high school students, which are really senior upperclassmen in undergraduate now, who I had the pleasure of mentoring throughout the COVID pandemic. And to this day, still write a lot of letters of rec and support them in whatever way I can. But now, Jasmine, Lake, and Ryan are doing fantastic things at Stanford, Princeton, and Johns Hopkins, respectively. The collaborators throughout the lab, both within the Congress lab and outside, Professor Ali Baim, who's Claire's advisor, who helped a lot with the support for the serial organization, as well as Kwasong Hong and Hanswei, who helped with the material characterization for a lot of the nanoplatelet work. Mahesh Gangashetty, who was previously within our group at the Rowland Institute, but is now faculty at Mississippi State, who helped with the manganese dope perovskite LEDs. Fang Liu and Ashley Saunders, who are here for a lot of the conversations on the integration of chiral perovskites into the materials for spintronic applications. Previous collaborations with Mark van Gersma and Chi-Tong Lee, where we looked at the integration of plasmonic electrodes within perovskite materials. And as well as I want to briefly highlight Beverly and Jose. So Beverly taking a lot of the administrative work to heart within the group, as well as Jose, who has helped really set up a lot of the heavy machinery and equipment and making sure that everything was up and running within the group as well. Okay, I also want to thank the mentors that helped me get here. So here is Professor John Kressler and Jeff Davis, who wrote letters of recommendation for me to get to Stanford and continue to do so today. But that really inspired me in what what electrical engineering can be, what semiconductor devices can be, and just got me really, really excited for research and the impact that I could have. As well as within Professor John Kressler's group, I have to give thanks to the PhD mentors that I have, which are really outstanding. So Upali, Adrian, and Victor, who helped me really get a good taste and refine my fundamentals for semiconductors, but also really support me when it came time to apply to graduate school. So they were the stereo before the stereo for me. So they helped me write my SOPs and balance interviews and kind of these things that I had no idea about as a senior undergraduate student. I also want to thank the teachers that don't often get their flowers. So the ones that I had in high school that really influenced me in a great way. So here, Lori, Elizabeth, Jeff, and Dottie, who were from the math department and really opened up my eyes to the STEM field, as well as Thomas and Rebecca, who showed me the potential interplay with math and also computer science and physics and how that would eventually manifest itself as an engineering. And as well, I think a lot of you know that I am a violinist. I've been playing for over 20 years. And so my orchestra conductors as well, while I might not play as professionally today, the key interpersonal and leadership capabilities that they give in me has really paid dividends throughout my time here at Stanford and also at Georgia Tech. Okay, cool. And then I have to thank all my friends that are both here at Stanford and in Atlanta and everyone in between for all your support and for helping me throughout this period of time, as well as my family. So I think my dad is here. You can go and talk to him and figure out what's wrong with me if you want to. But I also have to thank my mom and my two sisters, as well as my extended family back in Peru, and as well as joining Claire's family very soon. And lastly, really thank my roommates. So I have in my own household, I have the minority eye color of a brown eye. Both my roommates have blue eyes. But I really am thankful for the amount of peace and support that I've gotten from Claire and Ollie throughout these years, and has been really, really important throughout the PhD. So yeah, I think that's it for me. Thank you.
This concludes the public portion of the event. Thank you all.
Make sure you close the public Zoom.
Yeah. Okay.